Hello everyone, welcome to Math Side Trips, a channel for math teachers, students, coaches, trainers, and enthusiasts. Thank you for sparing time and effort to visit this channel. Many of the topics that have been discussed and will be discussed in this channel are those that are not usually taken up in mainstream classroom instruction. We hope that you will find in this channel something new, interesting, or useful. This is our channel name, Mathematical Side Trips. In this video, discussion will focus on construction of equations in one variable, in particular equations involving square roots. I am Napoleon A. Gacking Jr., a math teacher. In the preceding video, construction of polynomial equations and equations coming from identities have been discussed. For polynomial equations, a solution is embedded by considering a particular value and hiding it behind a variable, say x, and obtaining an equality of expressions in terms of this variable. In this and upcoming videos, construction of equations involving radical expressions will be discussed, namely equations involving square roots, involving cube roots, and involving fourth roots. For now, we take up equations involving square roots. Consider the number 5. Then we may write 5 equals 2 plus 3, which is square root of 4 plus square root of 9, or 5 is equal to 9 minus 4, which is the square root of 81 minus square root of 16, or 5 is equal to the square root of 5 times 4 minus the square root of 4 plus 7. Now, embed a particular value represented by x, say x equals 4, and express some expressions in terms of x. Then the above identities turn into the conditional equations. Okay, so the 5 equals 2 plus 3 becomes 5 equals the square root of 5x minus 16 plus the square root of 4x minus 7. Before we proceed, take note that 5 times 4 is 20, minus 16 is 4, and the square root of 4 is 2. And 4 times 4 is 16, minus 7 equals 9, and the square root of 9 is 3. Or using the subtraction, 5 equals 9 minus 4, we have this. So 81 is equal to 20 times 4 plus 1. So we have 20x plus 1 here in the first square root. And in the second square root sign, we have 5 times 4, which is 20, minus 4 is 16, which is whose square root is 4. And the third one, we also have expressed 5 in terms of x. So here we have square root of x, which is square root of 4, which is 2, plus 3 equals 5. And on the right hand side, we have 5 times 4 is 20, plus 7 is 27, minus 2 is 25, and the square root of 25 is 5. This among many other possible equations involving x. Despite differences in appearance, each solution set contains x equals 4. Exploring further, other possible equations include, but are not limited to, okay, we have 2x minus 3 equals the square root of 6x plus 1. Okay, on the left side, 2 times 4 is 8, minus 3 is 5. On the right side, 6x is 6 times 4, which is 24, plus 1 is 25, and square root of 25 is 5. So we have that one, and then we have this another equation where we have a quadratic expression inside the square root sign. Here we have a double square root. And we have here, we have a square root under another square root, which is under another square root sign. Again, each of the equations has solution sets that contain x equals 4. Care must be taken to avoid getting constants that are too large after clearing of radical signs. For example, construction could have proceeded as follows. Okay, 5 is equal to the square root of 25, which is eventually equal to the square root of 3 plus the square root of 480 plus the square root of 16. So with x equals 4 embedded, we produce the following equation. Square root of 3 plus the square root of 120 plus the square root of 6x minus 8 inside the second square root sign, and the whole thing equals 5. Now, clearing of square root signs, because this is perfectly solvable, we get the quadratic equation 2400x squared minus 19,361x plus 39,044 equals 0, which is a quadratic equation but not a very nice quadratic equation because of the very large coefficients and constant term. Also, introducing x or x squared inside a radical sign at will may result in an equation that is too unwieldy to handle for a student just starting to learn how to solve quadratic equations. A list of patterns that will guide the teacher in the construction of equations involving square roots will be given shortly. First, let a, b, c, d, e be constants, h of x, k of x, l of x, and m of x be linear expressions involving x, and q of x, q sub 1 of x, q sub 2 of x be quadratic expressions involving x. Then the following is a list of patterns that one can imitate in the construction of equations involving square roots. So the first one, very simple. A is equal to b times the square root of lx, and the other one, a is equal to b times the square root of q of x, which is a quadratic expression. Then we have the second, we have the third pattern, the fourth, fifth, there are two, sixth, seventh, eighth, we have ninth, 10th, and 11th patterns. Although patterns 6, 9, 8, and 10 and 11 are essentially the thinly veiled patterns 1, 4, 7, and 9 respectively, they are listed as distinct patterns because they give some semblance of variety, particularly to those who could not at first glance spot the similarities. Note also that pattern number 7 is in turn a thinly veiled version of pattern number 2. The list is not by any means complete. Other possible patterns have been avoided on purpose because they have the propensity to become too unwieldy for the students to handle. 6 sample constructions of pattern 11 are shown below. So using the seed equation, 4 equals the square root of 7 plus 3 times the square root of 13 minus 2 times the square root of 4, we have using x equals 3 as an embedded solution, okay, we have these three possible equations among many others. So we have that one. Note that 4x plus 1, 5x minus 2, 3x plus 4, although they appear differently, but when you substitute the embedded value x, they are equal in value. Similarly with quadratic expressions, 2x squared minus 5x plus 1, 3x squared minus 8x plus 1, and x squared minus 4x plus 1, meaning that they can be switched or interchanged, resulting in another or a new equation. Now, those three, after clearing of radicals, simplify to the quadratic equations. Letter A, 2x squared minus 11x plus 15, which is equal to the product of 2x minus 5 and x minus 3. Letter B, x squared minus 6x plus 9, which is the square of x minus 3 equals 0. And then letter C, 5x squared minus 14x minus 3, which is the product of 5x plus 1 and x minus 3 equals 0. Obviously, given any particular pattern, there is no limit to the number of ways a seed equation can turn into an algebraic equation. Note that there are three distinct linear expressions inside the radical sign and outside the third, and three distinct quadratic expressions inside the third radical sign. Since only one pattern is used with the same numerical values appearing, corresponding expressions have the same value as I have explained earlier. So we can actually have 6 more equations, or a total of 9, by simply switching corresponding expressions. For example, by switching the expression 4x plus 1 from equation 1 and 5x minus 2 from equation 2, we get the equation or equations, these two equations. So we now have additional 2 equations by simply switching 5x minus 2 and 4x minus 4x plus 1 rather, which correspond respectively to the quadratic equations 17x squared minus 110x plus 117, which is the product of x minus 3 and 17x minus 39. And the second equation simplifies to x squared minus 8x plus 15, which is the product of x minus 3 and x minus 5. Again, showing that the embedded solution, x equals 3, is there. It appears as one of the solutions. We could have started with the seed equation. 4 is equal to the square root of 10 plus the square root plus 3 times the square root of 1 plus 3 times the square root of 1. Then using x equals 6 as embedded solution, the three more equations are okay, so we now have 3 more using x equals 6 as a solution. And clearing of radical signs, we get this quadratic equation and this. So we have 3 quadratic equations, each of which gives x equals 6 as a solution. Just like before, we could have had 6 equations more, if we wanted them. This is all for now. We hope that you have again learned something new from this video. Please hit that subscription button if you want to subscribe, and smash that notification bell for updates about upcoming videos in this channel. God bless.